Hello, welcome to another software short video. Today's topic is called What is cFS, the Core Flight System? And by way of some animated PowerPoint, I'm going to do a brief intro, go over the cFS layers and the components of cFS, give some examples on how to architect a system with the cFS, and provide a ton of links. What is cFS? It stands for Core Flight System, and although some people, like myself included, occasionally call it core flight software, as it is software. There's a small c there indicating, I believe, the lightweight, small nature of the core. It's an open source, reusable, embedded, real-time flight software framework. And I have the word flight here in brackets because really this is more, it doesn't have to be an aircraft or a spacecraft. It's much more general purpose than that, really to general real-time embedded systems. It was developed by Goddard Space Flight Center. And really, I have to hand it to Goddard. Goddard, like all other space centers across the agency, prior to this framework, were in this, if you look on the right, this clone and own period, where every time there was a new project, you would try to either rebuild software from scratch or try to assemble pieces from a previous mission. And really, that's really not the way to go, right? So I have to hand it to Goddard. They carved out time and good people to determine a common denominator, a least common denominator of functions that would be needed, and they architected this system, which you see here. It was first used on the LRO spacecraft in 2007, and it has proliferated since. So I have just some words here on why to use it. Well, it saves time and money. You don't have to reinvent the wheel every time, rebuild software that's common across spacecraft. You can concentrate on your mission-specific code. Plus, it promotes reliability because it's been tested and used on multiple projects. There's commonality between projects and skills between people, and supporting tools. So it is a NASA agency asset for flight software reuse. It's used quite heavily across NASA. Many NASA centers use it. I have a listed there about 40 projects that have or are currently using cFS. It's probably not an exhaustive list. And since it is open source, it has been picked up also by other government agencies, DoD included, and it's being used in academia, some private companies listed here, and many international space agencies are using it for their projects too, especially ESA and JAXA. Some key points is that it is broadly applicable. You see on the pie chart here, it can be used for Class A safety critical human rated code across an entire spacecraft, or could be used just simply for a single instrument and plugged into a more complex system. I have some qualities listed here that I'm going to go over on the next chart, but in general, it's lightweight, compatible. It's written in C, about 9,000 lines of code for the CFE layer that I'll go over. It's configurable and data-driven. It has a bunch of reusable apps and support tools. And as a user, what you do primarily is configure the system and plug in your apps, similar to plugging in apps on a phone. And it does work on multi-platform hardware and operating systems, which I'll go through on the next slide. So let's get into the architecture. I'd like to go through it all on this one slide. So let's start at the bottom with the platform support package, the PSP. This is an API layer that allows apps above it to run on multiple hardware platforms without changing the code. So if you run on a different platform, you basically swap out this layer, and there's a list of some common PSPs listed here. Above that is the OSAL layer, the operating system abstraction layer, and that provides a level of abstraction between you and the operating system. So you could run on multiple operating systems just by switching out this layer. And that turns out to be a really strong feature in development because you could develop on Linux, say, and on a PC, but then deploy on a flight system like VxWorks with maybe different hardware below it. And that was a list of some of the OCLs that are common. Above that is the CFE itself, which provides a bunch of common services that are available for apps to use. And now I'm going to go kind of on the right-hand side here. The first of these services is called the software bus, which is a virtual software bus that provides a publish, subscribe message service for apps to send data and subscribe to and receive data from each other. And so this provides things like, publish, subscribe. Time services provides just that, things to do with time. There are timers, ways to link to GPS devices, ways to do a delay, things like that. Executive services control the tasking, starting and stopping, things like that. Event services is a bunch of services to allow for asynchronous event communication between apps and possibly between your system and the ground. Table services is a key component that provides for the data-driven aspect of this architecture. So as a user, you should try to make apps data-driven such that you read in a table and that configures the app so that you don't have to change the code itself, but normally the table. So this has things like, read a table, write a table, swap tables. And then there's some other services listed here. Above that, there are several reusable apps that are available within the cFS ecosystem. They're listed in I think on the last chart as references, but there's a few of them here that I was going to go through. Namely, the scheduler is kind of what you use to plug your apps into the system to configure it, tell it how often you want your apps to run. And that is configured with a table. So as a user, you would put your app into the scheduler table, the scheduler would read it and then orchestrate your system as you've described. Telemetry output provides output data outside of the system, and command ingest receives data from the outside. These two come with samples, and they're usually highly configured by the special mission that is being used. Then there's this CFDP that provides for the uplink and downlink of CCSDS files, and the file manager manages those files on the storage device. Another handy app is the DS, the data storage app, and that is configured with a table to subscribe to data on the bus that you're interested in recording, and then send it to a configurable storage device. There's also an app for limit checking if you go outside of bounds that you might want to be alerted, and health and safety manages how the system is operating and if there's any overruns. So all of this provided that you see on the screen right now is the reusability aspect of this system. You get all of this, and then as a user, what you do is add what I just showed in yellow, and that is the mission-specific apps, the apps that make your system unique. And I've separated them out into two flavors: mission-specific apps. These are higher level apps that might be like GNC, your guidance, navigation, control, propulsion. And then to lower level apps that talk directly to maybe sensors or effectors, the hardware on your vehicle. So all of these you would write for yourself. And the way they would normally work is you'd plug them into the scheduler. You maybe read from a sensor. The sensor would publish on this bus. Some app would be interested in that, would subscribe to it, ingest that data, do its calculation, publish back on the bus. Then maybe another I/O app that does affecting might read from there and then provide output. So that's a little sample of how this is a reusable system. And as a user, you would plug in these apps and choose which of these reusable apps to take advantage of. So let's take a look at a real life example. This was taken from the Morpheus lander flight software back in 2013. I was the project lead for this, and I think it was the first project at Johnson Space Center where we brought in the cFS, and it worked out so well that many subsequent projects started using it. But this gives you a real world example of what was really on the vehicle represented here in a bubble chart of the software architecture. You see some familiar things on here. So the blue apps were the reusable apps that we really did reuse and configure. And the green, of course, all the services that are provided were used. So we started with the blue and the green, and we had to add the pink and the yellow. So as I mentioned on the previous chart, we have two flavors of the things we added. One is in the I/O kind of area, and one is in the non-I/O or app area. So the I/O apps are all pink here, and you can see this vehicle had multiple IMU sensors, and it actually actuated the propulsion system, the valves, with this A to D I/O. And you see the rates at which these are running here too. So this was running at 100 hertz. Some of these are running at 10 hertz, some here at 50 and 5. So this is how you can configure your system with the scheduler. And then the apps that we wrote were really nicely separated, because you could assign different people to one or more people to each of these apps to be plugged in. And we have here the G for guidance, and then the N, nav. These are all the nav functions, the C for control, and then prop, the propulsion app. And then we had it all controlled, orchestrated, if you will, with an automated flight manager. So this is a real world example of a cFS use, and seeing as that was 10 years ago and it's still being used today, I think the framework is quite relevant. And here's just another quick look at an alternate architecture using cFS in a distributed system, just to give you the feel for the fact that this can be used over a network. And the thing that accomplishes that is an app called the SBN, the Network Software Bus. And you can put one of these SBN apps in your cFS system, or even use just a library in a non-cFS system to accomplish the publish subscribe method and this whole framework across a network, just to give you an idea of that. I just wanted to give a little bit broader of a software architecture picture across an entire project instead of just focusing in on the flight software. So as you're probably aware, when you build a flight software system, there's a lot of components that come into play. You have the flight software, the stuff that actually runs on the vehicle on the top. You have, to the bottom left, you have sim software, simulation of the vehicle, so that you can develop the flight software and test it. You have ground software that controls it in real time while the flight system is in operations. And then you have a whole tool set, right? So these are usually, it's called the triad, but plus the tools. It's really 4 major components of a complete software architecture that are pictured here. Now, this is again an example from the Morpheus project, but you can see how the reuse plays into this. Of course, I went over the flight software and the layers that would come there. But the other point here is reuse can also is also very useful in the other components, right? So in simulations, at least for the Morpheus project, we had a lot of reuse, which are also open source NASA products that I'll give the links to. So we use this trick simulation, and trick and cFS play very well together. There's another Goddard simulation, I think, called 42, and there's probably more that work well. And then there's several ground systems that I'm going to give the links to. In this case, we used an one called ITOS, which was also reusable. So you can see that if you have to build a system on short notice and you have to rebuild all of this, it would, you wouldn't have enough time or people probably. So I think we're forced into, and it's even better, we're in the world of reuse, and having products that are built for reuse, such as the cFS and these others, for use on multiple projects is really the way to go. And then there's the tool chain, and this was 10 years ago, but similar tools are used today. And I think on the next page, I'm going to go through the list of all the supporting tools that work well with cFS to make this whole system happen. On this last chart, what I just wanted to show and give links to is all the cFS itself, along with a ton of other tools and supporting code bases. The first link is the main repo, and from there you can go to the wiki and sign up to be a member of the community of practice. There's some distributions that are available, and when you call it a distribution, it actually comes with cFS, a ground system, and a SIM. So it's like a complete system in a box. But separately, for larger projects, you can pick your ground system. I have 1, 2, 3, 4, 5 of them listed here. And the 2 simulations that I mentioned, Trick and 42, I'm sure there's more. This can get you started. And then there's all these tools and supporting libraries. So these interfaces, there's an interface with Simulink, if that's what you'd like. There's also some libraries for IO and SBN, as I mentioned. And then some of these tools can help make your system possible. There's a test framework to unit test and test your commands and telemetry. There's a data dictionary tool. This is how you define all your commands and your data and pack them, and how they're going to go in and out of your system as the authoritative source for data. There's utilities for performance. So there's a lot of support tools out there to help make a cFS system possible. And then last, I'm going to just throw up the reusable apps that are online and available to plug in. This concludes the video on cFS. I hope you found it informative, and feel free to check out the ton of information online at some of the links provided. And as always, I'm open to questions, comments, and suggestions for more of these videos. Have a good day.